All right, I wanted to show you a little bit more about this unbelievableness. And I know I talked about it, but I just wanted to, I pulled a picture out of the RMA paper, and I wanted to point to one other paper about this, right? So again, there's this kind of history. This is about regression, which you've learned in various ways, a very simple thing, the ordinary least squares regression. There's a beautiful version of it in linear algebra, which couples with the calculus approach. Oh, I know, I need to be on, let me find this, yeah. So let's just quickly refresh very, very quickly. So, and I just want you to sort of know about this, right? So this is the normal regression. So you think the errors are going to be this way, and you fit a line of best fit that minimizes the sum of the errors squared. That's one way to think of it. We use square because we can differentiate that thing, right? Absolute value would be totally fine, right? That would make sense. You want the error to be just the absolute, that's the error. But square is, yeah, works out, yeah. And the invariances turn out to be good things and all sorts of stuff, right? So squares are not quite as big a hack as I'm perhaps suggesting. This is if you did regression the other way, right? So this is the errors are all in X and the regression is X on Y. And then there are various other kinds of things where you're trying to minimize something with respect to the line of best fit. But RMA, reduced major axis, or it's standard major axis now, I think, is generally what it's accepted as, is minimizing the area of these triangles. So you're going to have a line of best fit, you mess that around with that, and then you want that line to be such that the sum of these areas, or you could make the rectangles, is as small as possible. And this, surprisingly, is the only scale independent one, which is really weird, right? And that's the work by Samuelson. So there's a difference, there's a completely separate thread in economics, right? In the 1930s, this guy Samuelson, Nobel laureate, very famous, figures the same story out. And so now we have that tied together. But this is the 80s, 50 years later, completely separate sort of line. And I looked back in RMA. RMA doesn't talk about Samuelson at all, right? That's just anyway, so this is a beautiful thing. And I just sort of wanted to reinforce some pieces about it. The other aspect, so that's how it works again. And then there was this extra piece where you figure out that in fact, the slope of this line, we have some cloud of points, the slope of this line is actually the standard deviation of the y points, right? If you just calculate the standard deviation absent the values of the x values, and then the standard deviation of x, so it's basically, what's the sort of rough shape of the rectangle that this cloud of points sort of makes. It's just the ratio of those, so it's very easy. You don't even have to connect the x's and y's, you just take them as separate things. So in fact, which is kind of super weird, and I know I'm just sort of repeating this because it is kind of a weird thing, if you just have an evenly distributed set of points in x and y, line of best fit will be this, but it could be plus or minus, right? There's a plus or minus you always have to figure out. So even if it'll still give us something, right? Okay, but of course the correlation coefficient here is 0, there's no correlation. So one of the upshots here, and I added this to the slides, and this is an example from RMA. I'm going to point to Labarbera, this paper by Labarbera as well, where he goes and does the same kind of thing. I'm going to mention this in a second. So if you find an old paper or any paper and they've done least squares, so this is a terribly messy looking thing, and you've found that they've done ordinary least squares and reported a slope, so that would be ordinary least squares. Here is this one, right? That's the annotation, the notation in this paper. So this slope is shallow, but if they've reported that, drawn a line through it, but also given you the correlation coefficient, right? They've also reported R, then there's this very nice thing that you can actually just deduce the RMA thing, because the RMA slope is this slope, y on x, divided by the correlation coefficient. So if you have a paper that's filled with slopes and correlation coefficients and they don't know about this standard major axis thing, they've just said, oh, we're just going to do this regression over and over and over. But you know that there are errors in both of these measures, that you really can't treat this as an independent variable, it's measured beautifully, then you can go through and actually systematically correct it. Or figure out what the this slope is for the model where you assume errors in both quantities. So that's a really kind of cool thing. So that's, and just there are some calculations here, right? So the slope, so here's the correlation coefficient in here, it's 0.35. So you can see, there are two things here, right? We're going to multiply, so 1 over r squared, this is a pretty big r squared and 1 over r squared. That's the difference between the regression of y on x and x on y, right? Those two slopes, they kind of give you the bounds of the slopes that are possible. Like if for some reason you think this is the dependent variable or this is this one, this is how variable things could be. And that's a pretty big range in this case. It's a factor of 5 or a factor of 0.2 closely, roughly. So if you just had correlation coefficient is here, it's the 0.43. You knew, I think it's here. Here's say this correlation, 0.334. You'd divide it by the correlation coefficient, and that would give you the RMA one. And then you could divide it again, and that would give you the slope for the x on y thing. So that's sort of helps sort of salvage a lot of papers that are floating around that just sort of, where people just sort of use this standard least squares thing when they shouldn't have. It's pretty good. Okay, yeah. So that's all in there. And that's, I've sort of just written this, right? So the upshot is that if you just have ordinary least squares and you have the correlation coefficient r, then we can figure it out. So that's good. La Barbera, he goes through and sort of points to a lot of papers, digs out their data and says, fix these things up. From what I understand, and West, who I've been talking about a little bit, and I'll remind you, he'll come back again, Jeff West, actually told me that I think this guy resigned from the Science Magazine Board of Editors over West paper. We're going to get to West paper in a little bit. This is a paper that had, I believe, 9 reviewers, super controversial, including someone who said, that's it. You publish this, I'm gone. So, yeah, interesting.